Okay. Okay. So, welcome to another JAM chemistry syllabus teaching. Um, and today we are going to be looking at a new topic, and the topic that we are considering today is actually nuclear chemistry. Nuclear chemistry, and I remain your tutor, your teacher. In this series, my name is Anjorin Oluwafemi Excel. I hold a BS in chemistry and a postgraduate diploma in education, science education to be precise. And I also hold a master's degree in environmental and analytical chemistry. And I'll be guiding you through what nuclear chemistry is. And I want us to start off with our learning objective for this lesson. Um, Learning objective. By the end of this lesson, students should be able to, one, define radioactivity and identify types of radioactive emission. That's the first goal. The second one is that we should be able to describe the properties of alpha, beta, and gamma radiations, and then write and balance simple, nuclear equations, and differentiate between natural and artificial radioactivity, and be able to calculate the half-life of radioactive substances, and then apply the knowledge of nuclear chemistry to real-world applications. So these are the things that we're going to be covering in the course of our lesson on this topic, nuclear chemistry. So let's start off with nuclear chemistry and talk about radioactivity and give a simple definition of what radioactivity is. So radioactivity basically is the spontaneous emission of particles or electromagnetic radiation from the unstable nucleus of certain atoms as they decay into more stable forms. So that's what radioactivity is basically. It is just simply the spontaneous emission of particles or electromagnetic radiation from the unstable nucleus of certain atoms as they decay into more stable forms. Okay. Having said that, the next thing that we need to look at are the types of radioactive emissions that we have. What are the types of radioactive emission? The first one is alpha particles. Alpha particles, they are the first type of radioactive emissions. Basically, alpha particle is composed of two protons and two neutrons. It is typified with the helium nucleus. That is what we use in characterizing it. So it has two protons and it also has two neutrons. It has a charge of +2. It has a charge of +2. Alpha particles also has a mass number of 4, and that's why we characterize it with the helium nucleus. That's the 4,2 He, symbol, that we use in characterizing the alpha particle. So it has a charge of +2. It has a mass number of 4, and not only that, in terms of penetration, it has low penetration and can be stopped by paper or skin. So very, very low penetration when it comes to alpha particles, okay? And then in terms of ionizing power, it has high ionizing power. Alpha particles have high ionizing power, very, very high ionizing power. So those are the properties of alpha particles. So that's the first type of radioactive emission that we have. The second type is beta particles. The beta particles is the second type. And it is composed of electrons or positron. That's electron, that's the beta minus, and the positron, the beta plus, emitted from the nucleus. So that's beta particles. And it carries a charge of -1 when it is an electron, or +1 if it is positron, as the case may be. Another thing again is that it has a mass number that is approximately 0. It has 0 as its mass number. And penetration, in terms of penetration, it's moderate. It has moderate penetration, compared to alpha particles. It is stopped by aluminum foil. So if you look at it in comparison to alpha particles, you discover that it has a better penetration than alpha particles, and that's that for that. So in terms of ionizing power, so it has a moderate ionizing power. Now, when there is a beta emission, what happens is that our mass number, it remains the same, but the atomic number increases by 1. For an alpha emission, the mass number increases by 4, then the atomic number also increases by 2. Okay. So the next one is gamma rays. Gamma rays are high energy electromagnetic radiation, very, very high energy electromagnetic radiation. So they are composed of high energy electromagnetic radiation. They have a charge of 0, a mass number of 0, and then their penetration is high. It requires thick lead or concrete to shield them. So you don't play around gamma rays because they have high penetration. It can be very, very disastrous, very, very deadly to the human organs, or the human body, as the case may be. And so that's for the radioactive particles. So ionizing power for gamma rays is also very low. They have low ionizing power. So we've been able to establish that. But let's just look at it at a glance, using the table as our comparison now. Looking at the properties of radioactive emission now, and then using a table to help us to just look at it at a glance. If you look at it using this table, okay, you see that in terms of radioactive type, and we are just differentiating it in terms of radioactive type, composition, charge, mass number, penetration power, ionizing power, and then deflection by magnetic field. So that is the we are using that to differentiate these radioactive emissions. So in terms of alpha particles, it has 2 protons and 2 neutrons. It is the helium nucleus. For in terms of composition for beta particles, it is electron or isotopy positron. And for gamma, it is electromagnetic wave. In terms of their charge, alpha particles is +2, beta particles -1, and then gamma rays have 0, charge. In terms of mass number, we can see alpha is 4, beta is approximately about 0, then gamma is 0. Then in terms of penetration power, alpha particle has low penetration power, beta particles has moderate, and then gamma has some high penetrating power. In terms of the ionizing power, alpha particles have high ionizing power, beta has moderate, and then gamma has low ionizing power. Now, in terms of deflection by magnetic field, you discover that alpha particles are deflected towards the negative plates. And the reason is because they are positively charged. Whereas beta particles are deflected towards the positive plates. And the reason is because they are negatively charged. Gamma particles, because it is neutral in charge, it is not deflected by a magnetic field. Okay. All right. So let's look at nuclear reactions now. Now, if you look at this, nuclear reaction involves changes in an atom's nucleus and are represented by nuclear equations, which must balance both mass number and atomic number. Now, so nuclear reactions are synonymous to the normal chemical reactions. You must ensure that there's a balance from the product side and the reactant side, or the reactant and the product side. There must be a balance in the mass number. There must be a balance in the atomic number, and so on and so forth like that. Now, when you look at alpha decay, is an unstable nucleus emits an alpha particles, and when they do that, let's pick for instance uranium-238. Uranium-238 with a mass number of 238 and an atomic number of 92. When it goes through an alpha decay, it gives us thorium 23490, to thorium 23490, that is thorium with a mass number of 234 and then an atomic number of 90. Now, if you look at it closely, you discover that the mass number of uranium is 238, while the atomic number is 92. But thorium has a mass number of 234 and the atomic number of 90. For us to be able to balance it, balance that reaction, you must know where to put the alpha decay, or where the nucleus atom, sorry, the helium nucleus will be. It will actually be wrong if you put your helium nucleus at the side where you have your uranium. It will be very, very wrong. The reason is because the equation will not be balanced. But if you put it in the side that has a lesser mass number and atomic number, like what you see with thorium, 234 plus 4 will give us 238. 90 plus 2 will give us 92. So it balances the equation both on the reactant and the product side. And this is an example of what a alpha decay. So you can see an alpha decay, being represented there. What about if there's a beta decay? A neutron in an unstable nucleus converting into a proton and emitting a beta particle. Now, take for instance, you have carbon-14. Carbon-14 now transiting to become what? Nitrogen-14. That's carbon-14 with a mass number of 14 and an atomic number of 6, and then nitrogen having a mass number of 14, atomic number of 7. When you see that closely and you see the beta decay that occurs, you discover that the atomic number of carbon has increased by 1 to become 7. That's to give us that of nitrogen. And that is how a beta decay naturally looks like. And there's no change in the mass number. The mass number remains the same. Okay. So the next one is gamma emission. For gamma emission, after alpha or beta decay, the daughter nucleus may be in an excited state and release excess energy. And release excess energy as gamma radiation. Now, example, when you have cobalt-60 like this, cobalt with a mass number of 60 and an atomic number of 27, then giving us nickel with a mass number, the same mass number of 60 and an atomic number of 28. What you see that there is that there's a beta emission, and then that is followed by a gamma emission. But the gamma emission does not really have so much effect like that, because it's like we said, it doesn't have a mass number, it doesn't have an atomic number, it doesn't have a charge, it's neutral, so to speak. But it's accompanied, that's the decay. And that's why we have a transition from cobalt-60 to nickel-60, but their atomic number differs by 1 because the beta emission is accompanied by what? Gamma emission. So that's why we said after alpha or beta decay, the total nucleus will be in an excited state and release excess energy as gamma radiation. So the gamma radiation that we can see there is just the excess energy that has been given off. Another thing that we need to look at is nuclear fission. When we have a heavy nucleus, when it splits into 2 lighter nuclei, then it releases energy. What has happened is called what? Nuclear fission, or nuclear fission rather. A heavy nucleus splitting into 2 lighter nuclei, and in the process releasing energy is what we call what? Nuclear fission. An example is when you have uranium-235. It goes through a nuclear fission by taking on neutrons, and when it does that, it breaks into barium and krypton. Barium 14156, that is mass number 141, and then atomic number of 56, and krypton of 92 mass number and 36 atomic number. Then three molecules of neutrons are also given off in the process. Now, when you look at this closely, you discover that this big uranium atom has broken itself, that has split into 2 nuclear, 2 lighter nuclei. And that is what you see featuring there. That is what we call nuclear fission, the splitting of a heavy nucleus into 2 lighter nuclei, and the release of energy, corresponding energy in the process, is what we call nuclear fission. Apart from fission, there's also another one that we call nuclear fusion. This involves 2 light nuclei combining to form a heavier nucleus, releasing energy in the process also. You can have deuterium and tritium, combining together to form what? Helium. And then they release energy, which is neutron that has been released. That is a fusion. Lighter nuclei, they come together, they fuse together, and then they produce a heavier nucleus, like what we can see, on the screen there. Okay, so that's for nuclear reaction. So the next thing that we need to look at is to compare between natural and artificial radiation. Natural and artificial radiation. Natural radioactivity, or radioactivity rather, please. Natural versus artificial radioactivity. Natural radioactivity occurs in unstable isotopes found in nature, such as uranium-238 and carbon-14. So they will occur in unstable isotope that is found in nature. The key word is that it is found in nature. Artificial radioactivity, on the other hand, is induced by bombarding stable nuclei with particles producing radioactive isotopes not found naturally. So it is induced by bombarding stable nuclei with particles producing what? Radioactive isotopes that are not found naturally. Example of this is when you have aluminum with a mass number of 27 and an atomic number of 13 combined, and then you have helium, which is like a kind of alpha particle, so to speak. When you bombard aluminium with an alpha particle, what you end up having is you have phosphorus 30 that is being produced. That's phosphorus with a mass number of 30 and atomic number of 15, and then a corresponding particle or emission that comes along with it. So it produces what? A radioactive isotope not naturally found. So when you do this to aluminium, you can produce what? Phosphorus, but it is not natural. Cannot be found naturally in nature. So that is artificial radioactivity. Okay. So the next thing that we need to look at is half-life. And basically, the half-life of a radioactive substance is the time required for half of the radioactive nuclei in a sample to decay. The time that is required for half of a radioactive nuclei in a sample to decay is what we refer to as the half-life. And for us to calculate half-life, we use the formula n equals to n naught half, T over T half, where our n is remaining quantity, our n naught is the initial quantity, and then T is the elapsed time, and T half is the half-life. Okay, that's the guiding formula that we use. Okay, let's look at this example that says that a 100 grams of sample of a radioactive isotope has a half-life of 5 years. How much remains after 15 years? How much will remain after 15 years? Don't forget, it has a half-life of 5 years. So the number of half-life would be what? 15 divided by 5, which would be equals to 3. Now, the remaining quantity, n, will be equals to what? Making n the subject of the formula now from this particular distance, will be equals to what? Our n naught, which is in this case the initial quantity, which is 100 grams, multiplied by, from our formula, half raised to power time elapsed over half-life. And that was exactly what we did there, or what I did. So when you do that, you end up having as what? 100 multiplied by 1 over 2 cube, which will be equals to 100 multiplied by 1 over 8. That will be 12.5 grams. So for this one, the quantity that will remain after 15 years will be what? 12.5 grams. I hope you understand that. Very simple, but if you don't get it, if it's not clear, just put your question in the comment section and then I will attend to it appropriately. Thank you. All right. So what are the applications of nuclear chemistry? One, it is used in medicine for radiotherapy for cancer treatments. So somebody has cancer, they'll tell, oh, you have to go through chemotherapy. Chemotherapy basically is just using radiation to bombard the cancer cell and to try to kill them off so that they will not thrive again. So that's radiotherapy for cancer treatments. It's also used for diagnostic imaging using radioactive tracers. Yes, that's another way we use nuclear. We apply the knowledge of nuclear chemistry in the field of medicine. As regard the industry, it is used in radiography for inspecting metal welds. We've welded a metal, we want to be sure that this metal does not have any crack or fracture in it, because it can be very dangerous if it has crack or fracture in it because of the the use of that metal. Take for instance, you are building a bridge and you are laying certain metals, maybe underwater or something like that. Or you know that it's going to be carrying a heavy load. You must ensure that there are no cracks, there are no fractures or whatsoever on that metal when it is welded together. So what do we now use to be able to know whether there's a crack or to inspect that metal weld is to just subject it through radiography, and then that will tell us it will tell us if the metal that was joined together through welding is perfect or it has an issue that needs to be corrected before deploying it and using it for whatsoever purpose it was meant for. And also for thickness gauging in manufacturing, that's another area that the knowledge of nuclear chemistry is deployed. In archaeology, is used for what we call carbon dating, carbon 14 dating. I want to determine the age of an artifact. It's old, it's ancient, and we just stumbled on it in an archaeological site. And you want to I want to determine how old is this particular manuscript, or how old is this particular artifact, as the case may be. What you just need to do is to do what we call a carbon 14 dating, and that gives us the information of how old or how the age of that particular material that was discovered in an archaeological site. For in energy, nuclear reactors for electricity generators. So we can also use the knowledge of nuclear chemistry for generating electricity. Although this must be done with good with this must be done with a lot of safety precaution put in place so that we don't have what we have in Chernobyl, whereby there was a nuclear reactor, issue, and that's caused a lot of problems to the community and the environment in general. So you can also use nuclear reactor for electricity generator, and these are some of the applications of nuclear chemistry. Now let's summarize this lesson, and in this lesson we have talked about radioactivity. We've defined what radioactivity is. We've tried to touch on the types of radiations that we have or radioactive emissions that we have. And we've talked about alpha, beta, and gamma radiation. And we've also touched on, we gave their properties anyway. We touched on their properties, we discussed their properties, and we made comparison between the three. We also dabbled into nuclear equations and how to balance them, ensuring that the reactant and the product sides are balanced. And then we looked at it vis-a-vis when a beta particle is emitted, when an alpha particle is emitted, and so on and so forth like that. We also looked at the half-life. So we looked at the concept of the half-life. We defined what it is, and we also used an example, a question to buttress, what half-life is and how to calculate half-life. We also touched on nuclear chemistry, and we looked at the application of nuclear chemistry in medicine, in industrial archaeology, and in energy production. So we have been able to cover that. And I think with that, we are good enough to be able to face the JAM questions as they would come. Okay, so I'm going to evaluate the class, but if you have questions on what I've been discussing so far, please feel free to just drop it in the comment section, and then I will attend to them as I see them. Okay, so let's quickly evaluate this class and look at this one that says that write the nuclear equation for alpha decay of polonium-210. So when you have an alpha decay of polonium-210, I'm not supposed to even put solution. Pardon me, I even put the solution again. Okay, no problem, but I will do that for polonium. So I'm going to give you another one for you to do for me. And what I want you to do for me is just to put the answer in the comment section, then I will look through it and I will react appropriately. So I'm using this as an example now. The equation for alpha decay for polonium-210. So what happens with this one is that there's a decrease in the mass number by 4 and a decrease in the atomic number by 2. And that is what you have for us to be able to have lead, which is 20682. Now, for you, I want you to do for me, write the nuclear equation for the alpha decay of thorium-234. Thorium-234. So write the alpha decay for thorium-234. 234 means that it has 234 mass number and it has atomic number of 90. So please work it out and let me know what the answer is in the comment section. Okay, so it's very important. Okay, the next one says beta decay equation. Write the nuclear equation for beta decay of iodine 131. When there's a beta decay, there's always an increment in the atomic number by 1. The mass number remains unchanged. So what I want you to do for me is for you to now write the beta decay, the nuclear equation for the beta decay of aluminum 2713. Aluminum 2713. So you tell me what the answer is. Okay, all right. All right. So the next one says that a 80-gram sample of a radioactive isotope decays to 10 grams in 24 hours. What is its half-life? I think I've also solved this one. So what I will do is this. You can just look through this. And then I'm going to now change this to another question that I want you to now solve for me. Now you are taking a 150-gram sample of a radioactive isotope. Please pay attention and listen to the question. Solve it and let me have the response or the answer in the comment section. So I said a 150 gram sample of a radioactive isotope decays to 80 grams in 24 hours. In 24 hours. What is its half-life? What is its half-life? All you need to do is just follow the sequence. Once you follow the sequence, you'll be able to get the right answer. So whatever you get, just put them in the comment section and I will let you know if you're right or not. Thank you very much for joining me in this lesson, and I hope you've gained a lot. So I'll see you in the next video. Stay tuned. Thank you.